is Pacific Hackers Conference in Silicon Valley. So email Irvin if you want to volunteer and get in for free. I recommend it. I won't be there. I'll be at the CPTC, which is happening at the same time. Anyway, so we're down here at 141. And what I'm planning to do today is just talk about quantum cryptography, quantum computing in particular. And so there is not a chapter in your book about it, but I'm just going to explain it with the way of a demonstration and a lecture. This is what I did my thesis on, was quantum tunneling, a very closely related thing. And so you should begin to understand quantum mechanics. If you don't know any quantum mechanics, I'll attempt to give you an introduction to it here. It is, if you find quantum mechanics disturbing and baffling, that's good. If you think you understand it, that probably means you did not understand it. When I went to grad school in physics, I talked to everybody, and we all agreed that the best book on quantum mechanics you'll ever read is the third one. The first one you read, you can't understand at all. The second one, you say, this is garbage, obviously this is wrong. And the third one, you finally understand it. It doesn't matter what order you read the books in. You have to be exposed to it several times before you begin to actually understand what it's saying. At first, it seems insane. So let's start with the first thing I found was that the Python libraries we're going to use are very hard to install. So the best thing is to use a cloud Python called Python Anywhere. This will work, and trying to install it on your local machine is very painful and very annoying. So let's create a beginner account. It seems it is loading. All right, so now I give the username, Sam Demo. All right, and a Sam Demo at Mailinator. And a password of, oh, I gotta have, I think there's rules. Must have, let's see. Let's just try this. Okay, it's settling for my simple password. Sam Demo is what I did. I agree to whatever and register. All right. I'll save it there. Doesn't matter. Welcome to Python Anywhere. There's a tour, only 7 steps. So there's a console where you can have Bash or Python. And then you can have files and web apps. I don't need those. And I don't need notebooks. And I don't care about labs. All right. So anyway, all I really care about is Bash and Python. That's all we're going to need. And you can come back and get files. You create an account, you're logged in, and you can save your files and go back to them. And that might be useful too. Now, we actually need to install a Python library that is not always installed. So we're going to use the Bash console. And then we can install it with the usual stuff, Python 3 -m pip install. First we upgrade pip. So let me tear this off and put it on the side. All right, so I open Bash. All right, now I have a Bash console to work in. And now I can execute that command to upgrade pip. And you see it's working, it's downloading stuff. All right. And now I have to install Project Q. And what this is going to do, of course, it's not going to make this into a quantum computer. That would require different hardware. What it's going to do is install a quantum computer simulator that we can use in Python to simulate one and see how it works. So we're installing this thing called Project Q, and I found it extremely difficult to install. And after tried to do it again a year later, it's broken another way. It's very picky. This online environment is much better than trying to get a local Python environment set up the way it needs to be. Python has serious dependency problems. All right, so while it's installing that stuff, I'm going to make q1.py. I'll make a couple examples, and then we'll talk about what it means. So it's building Project Q. Good. Good. The recording is going as it should. All right. I'm really glad to see this building a wheel. When I tried to do it before, it kept on crashing instead of building the wheel, and I spent a long time hunting down dependencies and fixing weird problems until I just realized there's no use I'll never get it working on students' machines that way. I just go to a cloud environment where everybody can get it working. And when I Googled for them, there's a bunch of free Python cloud environments like this one. So that's the way to do it.
Do they have any limits?
What?
The cloud servers, does it have any limits?
Yes, the question is, does a cloud server have limits? And yes, it does. It limits you to only so many CPU cycles. And doing this project will pretty much use them up, so it starts slowing you down. So you're limited to only do a certain amount of calculation per day, I think. Yeah. All right, so it's installing stuff, collecting stuff. All right. There we go. It has installed Python project Q. So now I create a file called q1.py that includes this code. And what this does is import some things from project Q, like measure and main engine. Then it creates a quantum engine. And now I create a qubit, allocate a qubit, which we're going to talk about.
The first line.
What's that? Yeah, this one, from project. Oh, I'm missing an F. Why, thank you, right at the start. I thank you. I didn't get the whole copy and paste right. Good. Thank you. All right, so here you create a qubit, and then you just measure the qubit and print out the answer. That's all this is going to do. So I save this, and I run it with Python. Python Q1. All right. So it creates a qubit, and then it measures it 10 times, and that takes a while. Okay, there it goes. It's installing. Okay, there we are. So a default qubit is created in state. When you create a qubit, it's in state 0, which is like a normal bit in state 0. And every time you measure it, you get 0. So if you measure it 10 times, all the measurements are 0. So that's not extremely exciting, but that's the simplest type of qubit to have. Now we're going to flip the qubit, and here's where we get to talk a little bit about how this stuff works. Normal bits are just 0 or 1, never anything else. So you flip them or you don't flip them. But qubits are analog objects that can be in a whole variety of states. They can be up here in state 0. That's what we just did. This green arrow indicates the qubit we were on. Or they can be all the way down here in state 1. Then it will always be 1. But they can also hold these intermediate values anywhere on this sphere, which is called the Bloch sphere. Like this state of Y, if they are in that state, then it has a 50% chance of being 0 and a 50% chance of being 1. When the qubit is not measured, it sits in an uncertain state called the superposition state, mixing some amount of 1 and some amount of 0, and with a hidden variable, this angle. And you can do calculations on it in that state, but when you measure it, it will collapse into either 0 or 1. And if it's in one of these superposition states, it has a probability of being 0 and a probability of being 1. So we're going to turn this into an uncertain qubit. What we're first going to do, though, is we're going to rotate it around the x gate. And here's the x-axis, but if we rotate it 180 degrees around the x-axis, this arrow will rotate all the way down here, and I will have a state of 1. I will move from a certain state of 0 to a certain state of 1. So that's what this does. This x operator rotates it 180 degrees about the x-axis. So that will turn the 0 qubit into a 1 qubit. So this is q2.py. All right, so first I create the qubits and measure them 10 times and print it out. And then I create them, rotate them, and measure them again. So I'll do Python q2. I got to spell it better. All right, got to still spell it better. All right, there we are. So originally it was always in a state of 0, now it's always in a state of 1. So what we've done now is just the same thing as normal computing, 0s and 1s. Now we want to reach a superposition state. So this is going to be Q3, and you see it's going to use an H transform. And the H transform, the Hadamard, is what moves it into that state where it's got a 50% chance of being 0 and a 50% chance of being 1. They call it a Hadamard transformation. So I do nano of Q3 and put in that stuff, and then Python of Q3. All right. And so originally it was in a state of 0. After I turned it into a superposition state, now half the time I measure it, I get 0, and half the time I get 1. That's what an uncertain state of a qubit is. So now that's quantum uncertainty, and this is the heart of it. This is why a qubit is much more powerful than a bit. A bit only has one bit of information, it's either 0 or 1. A qubit is an analog thing that has that whole Bloch sphere. It has a lot of information, and the amount of information is determined by how noisy your qubit is. And unfortunately, the current hardware that we have is really quite noisy, so there's not as much information in those qubits as we would need to actually crack serious RSA keys. But in principle, you could do that if we can get better quality hardware, and it's improving all the time. Now, another thing you can do with qubits is you have this property called entanglement, which does not exist at all in normal bits or in the classical world at all. It's a quantum mechanical property. And you do that with the C0 operator. So let's make this one Q4 and see how the entanglement works. All right. So this is going to make two qubits, qubit 1 and qubit 2, and then rotate qubit 1 to an uncertain state, and then use C0 to entangle qubit 1 and qubit 2, and then measure them. And it's going to do that 10 times. So let's run this one. Python Q4. All right. So here's the pair of qubits, Q1 and Q2, and one of them is not rotated into an uncertain state, and one of them is, but they're entangled. So you see, if one of them is 0, the other is 0, and the uncertain one sometimes is 1, and the other one is always equal to it. The C0 has tied them together. These two qubits are entangled, so the one that was in a certain state has inherited uncertainty from the other. That's what quantum entanglement does. Two objects are required to be together, and the simplest case in physics where this happens, the famous Einstein-Podolsky-Rosen experiment, if you have a excited atom, an atom can decay, and there are atoms that can decay and will create two particles, like a positron and an electron. Particle and antiparticle, and they then travel in opposite directions because the original particle was at rest. And so one of them, well, there's a spin property on an electron. One of them must be spin up and the other must be spin down. Since they were both created from an original particle of spin 0, their spins must cancel, and if they move apart and you measure one of them and determine that it's spin up, the other one must be spin down. So the measurement of this one causes this one to change. And that's called quantum entanglement. Two objects are entangled, so their relationship, even if they're spatially separated, their state is mingled together. And that property makes it possible to do amazing things like to factor numbers into their component primes. That's the kind of strange property that is not present in digital electronics that makes it possible to generate a whole category of algorithms. And those are going to break our encryption if we get qubits that are higher quality than the ones the hardware has right now. So now we want to make a pretty circuit diagram out of it. So we're going to make a Q5 this way. We're going to make a text file with latex. Text is some kind of graphics program people use in the open source world. It's a way to represent pretty pictures. So this is going to have a circuit drawer thing and draw it and create something with latex. So I'll run this. And when you run it, it's going to put weird junk all over the screen. I'll run it with this way normally to see what it looks like. Python Q5. If you run this, it runs, but it spits out this weird looking stuff. This is latex. This is some kind of printing language. It really ought to be run to a printer or something. So since I can't really read that, I put it in a file called q5.txt. And now I just need to find some kind of printing engine to print those text files. Now there are supposedly some command line Linux tools, but I couldn't make any of them work. So what I do is I just use an online service here, an online conversion service. This online conversion service will convert a text file to a PDF. So I can download this file. Now to get the files, I think you click the 3-bar icon and then files. I've now made a file called q5.txt, and you can download files from here. If you go to files, there you go. Here's my files, my Q1, Q2, Q5, and here's my q5.txt. And I can download it here. I think that's what the down arrow does. Nope, that shows it to me. That's not what I want. There's going to be some way to download it. Maybe it's this one. Edit. Maybe it's this. That's probably what it is. Click. No, that's still not doing it. And maybe if I right-click that and save target as, that might do it. Save link as. There we are. I'll put it in downloads, Q5 All right. There we are. Now I've got it. It got it as HTML, though. That's not good. I wonder what happens if I download this one. Save link as. All right, I'm having a problem here. Let's see what I've really gotten here. If I view this in Finder. All right, here it is. And now I open it in a text editor. Let's see what I got. I might have not really gotten the text file. I might have got some kind of web page. Yep, I got some kind of web page containing the text file. I didn't get the good stuff yet. All right, let me try again. Let's see if my instructions do me any good. Right-click the down arrow and save link as. All right, let's try that. Right-click the down arrow. Save link as. Save that, and we'll see what the... there's the text file. That's what you need. Okay, good. So now I've got the text file here, and I can now upload it here in this file converter, input file, choose file, downloads text file. There we go. And convert. Oh, I got to choose the output format, which will be PDF. There. Now I can convert it. And I can download my converted file. Let's see. I think it says, now I can download it. Okay, download. All right. It's now Q5. I will save that. And now I've got Q5.pdf. There. And so here it is, the glorious PDF. It's kind of small. I can blow it up. And there you see, I've got a simple little circuit diagram. Here's 2 qubits in state 0. This one's run through a Hadamard gate. This entangles them, and that's the circuit diagram for this sort of thing. So you can write code to do this, and you can get a pretty circuit diagram. And so that's just a few things to learn to begin to understand quantum computing. And let me, there's some flags you can find using these techniques, so you get a little practice with it, and begin to get used to this brave new world. So make a program that matches this, and run it printing out the bits. And you can make programs that match these diagrams and run it to get the answer, and you'll get a little bit of practice doing some quantum computing. If you want to know why it's valuable, the thing to look up is Shor's algorithm. Yeah, here's Shor's algorithm. This is the algorithm that factors prime numbers, factors numbers into their prime components. And there should be, a diagram of it. Well, let's get a diagram. Let me try, find an image. There we are. That's Shor's algorithm. All right. So you have a bunch of Hadamard gates. You have a bunch of entanglements. And you run it through a quantum Fourier transform, which is another circuit. And the point is, this algorithm, you can feed in data, which amounts to a n, and you will get p out. And it doesn't go through a series of steps and an algorithm. It just is like a guitar, where it resonates to the right frequency by the natural properties here. All right, can I explain all the gates in 5.10.2? All right. The Y, Z, and H, that's all there are. H, Y, and Z, sure, they're easy. And this is entanglement. The plus is entanglement. So this is entanglement. Y and Z are rotation, and H is a Hadamard gate. And if we go to the block sphere, which is somewhere around here, okay, so X rotates 180 degrees about the X-axis, Y rotates 180 degrees about the Y-axis, which would have the same effect for a qubit in state 0, but it will have a different effect if it's in some other state. And Hadamard rotates 90 degrees. I think about the X-axis. I'm not sure what axis it rotates about, but it rotates about 90 degrees, taking this blue one to the red. All right. So I hope that helps. And I recommend that you check this stuff out. It's all extra credit, sure, but this will begin to get you in the world. This is why you care. The reason we care is because of this. There is a known algorithm which, in principle, could solve factoring numbers into their component primes, and it could do it very fast. So fast that even if we made the key 16,000 or 32,000 or 100,000 bits long, it would still not be enough. So that's why RSA isn't considered doomed. When quantum computers are improved over the next 20 or 30 years or 10 years, no one knows exactly how long, all of RSA cryptography will be broken. because this does not have anything where you count the number of steps and you cycle through a certain number of cycles. You just need a certain number of qubits, and you need to be high enough quality, and then it will just put in the N and out will come P. So that's why we have to abandon this, and we're now in the process of developing quantum safe cryptography instead, which NIST is having a contest of them. And within the next year or two, we will have an official certified quantum safe algorithm, and everybody's going to spend the next decade migrating all their encryption from other public key systems over to the new one. And that raises another issue, of course, that you'll have to, if you have any old data encrypted with the old system, you will have to get rid of it and replace it with a new one before this gets cracked. Of course, it might not happen, but at the rate of quantum computing progress, it's very likely to happen. And you may notice that in America's Chinese embargo, we just announced we're trying to block China from making progress on quantum computation. Quantum computation is considered extremely valuable. Yeah, OpenSSL 9 includes a post-quantum algorithm. Wow, that's interesting. It's risky to do that because there isn't an approved one yet. I tried doing that. I tried adding it to my class a few years ago because I trusted the Google submission, A New Hope, to work, and it was blown away. Oh, you've got a link. Good. OpenSSH, released with hardening against future quantum computers. See, that's a risky thing to do. Let's see what they did. It uses, this is using X25519 key exchange. Oh, okay. I think what this is doing is not a quantum safe algorithm. I think what they've done is they've switched to the one recommended for the time believed to resist attacks enabled by future quantum computers. Okay. This is elliptic. Okay. Well, that's interesting. So they have this thing called streamlined NTRO prime. Well, that's very interesting. Okay. I'm glad you told me about that. I'll save that link. That's it's a risky thing to do. Several people have tried to include quantum safe algorithms, but nobody really knows which one is quantum safe right now. So you're guessing. It's sort of like using a beta product. But anyway, that's an interesting thing to know about. Anyway, so I'm going to stop the recording, and I'll just